doing well, and I'm really glad that you have joined us for our seminar today. So today we have Dr. Elizabeth Maroon, who is an assistant professor in the Department of Atmosphere and Ocean Sciences at the University of Wisconsin-Madison. And she is a climate scientist who uses climate models of varying complexity to understand how oceans influence climate variability and climate change. She did her undergraduate degree at MIT in physics and earth and atmosphere and planetary sciences. And I was very happy to see that you have a minor in music. I actually have a double major in studio art and geology, which makes no sense, but I couldn't decide. So I was happy to see that. That's cool. And then you went to the University of Washington, where you got your master's and your PhD in atmospheric sciences, working with Dargan Pearson and Dave Battisti, who a lot of us know well. And while you were there, you also organized the Graduate Climate Conference. And I know that at least some of my students have gone for a couple of years now, and it's a really, really great opportunity. So all of you graduate students out there, look into going to the Graduate Climate Conference. It's either at Woods Hole or at University of Washington. It's super cool. So then you graduated and did a postdoc at Boulder at the Cooperative Institute for Research in Environmental Sciences. And I just learned, did 1 year after your postdoc at NCAR, which is really cool. You have a number of she has a number of first author papers in the Journal of Climate, as well as contributions in GRL and Nature Geoscience, and all of them looked really interesting. So without further ado, I am going to hand it over to you.
Thank you so much for the kind introduction and for inviting me. I've been looking forward to this.
I'm super excited.
Let me see if I can share the correct screen. Can you see that? Yes, I hope. I can't hear you anymore. Can you see the? Okay, cool,
yes.
Great.
Sorry, mine.
Yes, thanks for the kind introduction. I also wholeheartedly encourage folks going to the Graduate Climate Conference. I was just one small part of the organizing committee. It was a big group effort. So I didn't single-handedly do that at all. No, not at all. So I'm excited to talk to you today about some of the work that I did while I was at NCAR. It took a bit longer to finish up. I actually just submitted this a couple of weeks ago. And you all are the first audience who's going to see this talk in its full form. I've given snippets of it at Ocean Sciences and in other forums, but this is actually the full story. So this is going to be pretty cool. So the name of the talk was the 2015 Subpolar Cold Blob Predictable. And I'd like to thank my co-authors, Steve Yeager, Gökhan Dambashoglu, and Nan Rosenblum for working on this with me. So a brief roadmap where we're going to go. First, we're going to have an introduction about how to think about climate predictions. What is a good framework for that? We're going to talk about the main tool that I've used in this, the Community Earth System model, which is NCAR's climate model. Well, not just NCAR's, it's the whole community led by NCAR. And then we're going to talk about a case study. So in 2015, there was near record cold conditions in the subpolar North Atlantic. Turns out our prediction system could not predict it. And so we're going to use this as a case to try to understand how do you improve our predictions for the next go round. So let's step back and just think about how could we predict some quantity in the climate or in weather. A first really good prediction is to use climatology. So you have some climate variable with time, and you just say, okay, we've got this probability distribution. And we know our mean is somewhere in here, and then we've got less probability in the lighter colors. So high probability in the middle, low probability occurrence on the edges. So you can imagine the observations are probably going to fall most of the time near the middle, and some of the farther rest of the time further from the edges. The climatology would be a first good prediction. If, however, you knew something about the initial conditions, of your forecast. You could have made a better forecast by initializing from that first point. And so in here, I've represented initial value predictability with this green swath of probability distribution. You can see that it's mean. It has some time variability. And at the beginning, the possible spread that you have, because you've constrained your forecast to what you had initially, is way narrower. Over time, that spread widens out, and eventually your initial value prediction looks very similar to what climatology is. So that initial value predictability wears off over time. But if you're at the first part of your time period, it gives you more skill in predicting what happened. So that's kind of the idea between a weather forecast. If we know what today's weather is, we start here, and we spread it out as we go forward in time. And so using climatology isn't as good of a forecast as using initial value predictability. So in climate change, in the climate problem, we also have an upward trend in our temperatures. You could imagine this climate signal is temperature, global temperature, some region, doesn't matter. And this, we have an upward trend most of the time. So our climatology, the probability distribution function that we expect, also should be moving upward in time. So the prediction that you might expect is going to go follow up an upward trend. So this would be a more skillful forecast than if you had just used a stationary today's climatology alone. And this is known as a projection if you only have this external forcing in here. This is what the IPCC writes about. This is what the coupled model and comparison projects do. They have this whole spread of models that give you a climatology that's moving upwards. But let's add that other piece back in. Let's say we had initial conditions and we know we have an upward trajectory in climate due to anthropogenic greenhouse emissions. We know if our initial conditions are here, then we can get a better prediction for what our observational line is, so this black one, if we initialize from the right part and we include in that an upward trend. So somewhere here at the beginning, you can see most of your predictability is coming from the initial values, but at the end, most of your prediction is coming from the boundary forcing or the greenhouse gases, things that don't have initial value predictability. So predictions in this middle range have some component of both. They have the external forcing, the greenhouse gases, but they also have your initial conditions. And this middle range for our climate is the decadal timescale. You have information from your initial conditions that is important, but you also have the upward trend due to greenhouse gases, which contributes to the prediction skill as well. So when we have an initial value problem, we call it a prediction, but we're on the end. So this includes like the weather forecasts, ENSO forecasts out to about a year. And when we're on the other side, when we're doing the climate change problem, we have projections. So this is, we're using a scenario where we expect our greenhouse gases to go up, and this is a forced boundary condition problem. So this is multiple decades, century, millennia. But in the middle, there are decadal predictions where you have a little bit of influence left from your initial values, but you also have some influence from the upward trend due to, in this case, greenhouse gases. And so the jargon that people use to distinguish between the two of these are predictions on this end, and then when the effect of the various scenarios become important, you just call them projections. But in reality, for climate and the kind of simulations I'm going to discuss here today, you're somewhere in the middle of this gray area. We're using information from the projections for the scenarios, but we also have an initial value problem. So we're calling them predictions. So how do you make a prediction? There's a lot of different ways. You could use I kind of branch them here into two different categories. We have statistical or empirically based ways of doing it. So you pull in your observed data and you say, I'm going to calculate a linear trend between them, and then that linear regression, that's going to be what our model is. So when you take the observations and fit something to them, a lot of examples here. So analog methods, linear inverse models, machine learning. These are all what I would call more statistical models. On the other end, we have physically based models, things that, so like numerical weather prediction or ocean general circulation models, things that have some representation of the physical system that underlies all of it. So in that case, I mean F equals MA, thermodynamics, all of those predictive models that are based on physical laws underlie these models, which gives you it can give you the nonlinearity that is inherent in the climate system in a way that we may not be able to do with statistical models. So by physically based models, I mean things like WRF or MPAS or GFS, so our numerical weather models, or our atmospheric general circulation models, ocean general circulation models. And then when you couple all of these together into the atmosphere, the ocean, a land model, a sea ice model, vegetation, ecology, you begin having this conglomeration of models that are called either climate model or an Earth system model. And these are very comprehensive that include lots of processes. And these are the type of model that I'm going to be using here. In particular, I'm using the Community Earth System Model version 1. On the left here, we have a schematic of the types of different processes that are included. So we have a full ocean model as well as a full atmosphere model. Both are comprehensive, so they're at the state of the art of the type of parameterizations that they include and the level of physics. So these are if you have a hierarchy of models where you're going from very simple, maybe energy balance models on one end to comprehensive models on the other end, this is the very complex version. So another cool thing about the Community Earth System model is that it has vegetation and ecology in some ways included in it. So this schematic, it gives you, has a little turtle in it. They don't have actual biology in this sense. They don't have physical mammals in the model yet, but there are zooplankton and ecology at that level included in the ocean model. So what a climate model does is we have all of the equations in the land, ocean, ice, atmosphere, and for biology, and then we discretize them on a grid. So we chop up the world into a bunch of cubes, and we calculate the equations at each cube, and then we have the grids talking to each other, so they communicate what's going on from one place to another. So you have each of these locations, you're solving the equations, and you can get all of the different processes that are demonstrated here. So when it comes to prediction in a climate model, we know from our study of the climate system that different components of the Earth system give us initial value predictability with different timescales. So the numerical weather prediction problem is this basically a problem on the order of a week. So after a week, due to things like the butterfly effect, the system is inherently nonlinear and chaotic, such that you cannot predict, the initial value predictability wears off over time. But the other components of the land system, because they evolve more slowly, can still see some of that initial value predictability later on. For example, with land, and by land system here, they're talking about things like variables like snow cover. You have a bump of predictability from land at somewhere along monthly timescales. And then beyond monthly timescales, because the ocean is even more slowly evolving, you can get predictability beyond a month, out even to years, depending on which part of the ocean system you're thinking about. And so this could be everything from El Nino to the Atlantic reanalysis overturning circulation, those kind of processes that can give you predictability. And because the atmosphere, the land, and the ocean are all coupled together, if the ocean processes are a source of predictability, because they're coupled together, you can also gain predictability in the atmosphere or in the land. And so there's many timescales you can see predictability at. You may have heard of things like S2S, subseasonal to seasonal. I'm going to be talking more on this timescale, the annual and the interannual, I2D. But the problem I'm actually going to pose to you today starts out at the subseasonal timescale. So one of the reasons why we think that we should have predictability on decadal timescales is because of what's going on in the North Atlantic. So in the North Atlantic, we have one picture of how we think the coupled North Atlantic system is working. Let's say we have a strong zonal winds some winter, in this case, maybe 10 years before a peak in the AMOC. So we have strong zonal winds. Those winds are going to drive turbulent heat fluxes such that you're pulling heat out of the ocean. By pulling heat out of the ocean, particularly in the regions of deep water formation, this schematic by Rob Wills is suggesting that the Labrador Sea is one of the key locations for deep water production, which has been called into question recently, but go with it for the sake of the schematic. It pulls out heat, you get deep water formation, water sinks. If it exits the Labrador Sea and spreads out below, then somewhere you have to be pulling in the mass to replace the water that's sunk. So the way that we think it happens is that you get a strengthening of the Gulf Stream, the North Atlantic current, such that you strengthen the AMOC, the Atlantic Meridional Overturning Circulation, to replace the water that's sunk. And along with a strengthening ocean circulation, you're bringing heat from the subtropics poleward. So as you bring more heat, you're having this whole large area of the surface ocean that's warming up. The atmosphere feels that. So you can have a low pressure in the atmosphere that affects different areas of the climate that weren't previously involved. So the ocean heat convergence is way up here in the subpolar North Atlantic, but you're driving a circulation response in the subtropics. And that circulation response warms up also what's going on in the subtropics. Any of the climate impacts that are attached to sea surface temperatures in the subpolar or the subtropical North Atlantic will then will feel the effect in this climate variability and respond. So in summary, the idea is that if we initialize our model at this time where we've already got this imprint of really strong winds and we've got deep water formation such that our water masses have changed and that's what we're initializing our model from, then down the road, this whole chain of events has to happen, which could give us predictability about 10-year timescales. And there's a lot of different processes that are tied to this Atlantic multidecadal variability. We think Atlantic basin hurricanes are correlated. So you get more frequent hurricanes in years when these sea surface temperatures are warmer. Similarly, you have more European heat waves and droughts when the Atlantic basin is warmer. And you tend to have a shift in where the rainfall occurs in the Sahel of Africa. So you can get Sahel drought depending on what the sea surface temperature variability in the Atlantic looks. A lot of the evidence in this chain of processes that I've described comes from climate models because our observations are still quite short for a multi-decadal variability signal. So there's still a lot of work that needs to be done to tie down all of these pieces in the chain as best we can. But there's been a lot of work in this area to pull all of this together. And our climate models are starting to show predictability in things like Atlantic basin hurricanes, heat waves, and Sahel drought. So in this talk, I'm going to use two large ensembles. The first is the Community Earth System Model, CESM Large Ensemble. And the second is an initialized prediction, the CESM Decadal Prediction Large Ensemble. Everything between these two large ensembles of climate simulations are the same, except that this one basically just gives us the climatology plus an upward forcing due to greenhouse gases, so it has the external forcing in it. This one has the same exact forcing, but we initialize periodically, so that the difference of these two climate model runs can give us how much predictability comes from the initial conditions alone. So what the Community Earth System, the CESM Large Ensemble looks like is they started out from a long 2,000-year control. They branch it off at 1850 and began applying historical forcing. 1920, they initialize 40 different ensemble members. And so what they do is they give round off level error. So that's like 1 × 10⁻14 Kelvin in the atmosphere to each of the different ensemble members. And then they all let them go. So like the weather problem, after about a week or two in the atmosphere, you can see that these have all diverged and start filling out the climatology. So you apply the greenhouse and aerosol, the greenhouse gases and the aerosol, the ozone that all occurred in this history, and then they apply a scenario for the future. In this case, a business as usual scenario, RCP, representative concentration pathway 8.5. And then this black line is just picking out what one ensemble member looks like, while the gray line shows the swath of all of the ensemble members. By having 40 ensemble members, it gives you a very clear, a robust quantification of what the possible natural variability could be in the future. So this approach gives you both external forced response, so the upward trend that you see, as well as the spread, the natural variability. So the Decadal Prediction Large Ensemble uses the same exact code base and the same exact forcing, but it runs it in a weather model-like forecast. So every year in November, you start off 40 ensemble members, one in 1955, once in 1956, and you run them all out as what's called a hindcast for 10 years. And then you can verify each of these 10-year-long hindcasts against what happened in observations. So that would be the black line. The ocean initial conditions, because we don't have a very good observational state of what the true ocean looked like in the 1950s, comes from a simulation, an ocean-only CESM simulation that was forced by atmospheric reanalysis. So this is a forced ocean sea ice or FOSI simulation. And so this allowed the Steve and the other climate modelers at NCAR to put together the full possible state of all of the variables. So not just temperature and salinity, but including things like dissolved oxygen, all of the chemistry and the biology that's also included in CESM. And so you can initialize the model with all of that, and then you can have predictions of not just things like temperature and salinity, but predictions of the biology in the ocean as well. And biology here, I'm meaning like the plankton fields. And it does have skil. So right here, I'm showing you the skil in the Decadal Prediction Large Ensemble, and that this is a quantity known as Anomaly Correlation Coefficient, ACC. Where it's red, that means good, you have skil compared to observations. These are on lead years, like 1 to 5 years in the future on average. So this is a 3-year lead. Here's a 5-year lead. We're averaging from 3 to 7 and 5 to 9. If it's you have an ACC of 1, that means you perfectly matched what occurred. 0 means you have no skil, and blue is even worse. You're doing the opposite of what occurred. So even out almost 10 years, you can see there are places where you have really having quite good forecasts with correlations above 0.8, particularly in the Indian Ocean and the North Atlantic. So we have 2 bars to, you could argue that all of this is occurring due to global warming. It's getting warmer. So as long as you have global warming in there, you're going to have good skil. Everything's going up. So we have 2 bars to get across. First thing we usually do is we compare to a persistence forecast. So this is, we compare the change in our skil, ACC, and then we compare it against each of these 3 times. You can see that in many places it's red, indicating that we are doing better than a more simple persistent forecast, especially out 10 years in the North Atlantic. And we think that's because of the kind of processes that I described earlier. The harder bar is to compare against the CESM Large Ensemble, which includes your upward greenhouse gas effect. And what you can see is that the improvement you get from the CESM Large Ensemble is much more mixed. There's areas where you can see that there's the DPLE does worse than what was in the Large Ensemble, but there's also one key location where you are gaining more skil in sea surface temperatures compared to just a climatology with forcing in it. And in this case, that occurs in the subpolar North Atlantic. So understanding what's going on in the subpolar North Atlantic is really key, because that's what could be driving prediction skil. And then there's been a number in the DPLE of examples, things that have been applied to and examined, things that are physical, like Sahel precipitation, European rainfall, but also a bunch of other biological and both a terrestrial and in the marine ecosystem. So if you're interested in these kind of Earth system predictability questions, I encourage you to check out these papers. So what I'm going to do is tell you about one prediction case study where I've used the CESM Decadal Prediction Large Ensemble and compared it to the CESM Large Ensemble to try to understand what happened and why things worked or didn't work. So this case study is the 2015 what's called cold blob. So this is from June, July, August in 2015. You can see there's this big cold anomaly in the subpolar North Atlantic, and it was near record. You can see there were maybe one or two other events in the North Atlantic that were just colder, but not by much. So as I showed previously, the subpolar North Atlantic is one place where the DPLE has particularly high skill, probably because it has a reasonable representation of the kind of coupled AMOC and atmospheric processes that I described. Except there's 1 year where our observations of sea surface temperature are falling outside the spread in the DPLE range. So that occurs in 2015 in the subpolar North Atlantic. And it doesn't matter if you're looking at year 1 predictions, year 3 predictions, year 5, 2015 is always an outlier. So this was a failed prediction. Not only did our mean, ensemble mean forecast, fail to capture that dip, but it's also falling outside the spread. So what happened? And so before I tell you what happened, let's back up and say, okay, case studies, those can be great, but what are we going to learn from this one? So there are 2 reasons why this case study is important. The first is that the subpolar cold blob contributed to the 2015 European heat waves through an atmospheric teleconnection. It's important to understand from a societal relevance and a climate impact perspective. The other is that we have this idea that if we have errors in a forecast at the beginning, then we're going to have errors later in our forecast. So if we get it wrong now, that's going to mean we're going to get our forecast wrong later. And in the subpolar North Atlantic, this idea seems to hold true. So in this middle scatter plot, I have lead year 1 error, so early errors, correlated against later errors. And so the blue dots are a 5-year mean error, and the orange dots are 7 years. There's a weak correlation. R is 0.44 or 0.36, so roughly describing 18 to 20% of the variance. So it's not the only thing going on, but if you compare it to if you just had the persistence forecast, so using, what happened yesterday is today's forecast, something like that, you see there's no correlation. If you had an error yesterday, that doesn't affect the error 3 years from now. But in the subpolar North Atlantic, if you have errors in the early part of your forecast, it does affect later errors. This gray line here indicates the error in the subpolar North Atlantic sea surface temperature that occurred in 2015. This event was the single worst prediction for lead year 1 in the DPLE. And so it's worth it to try to understand what happened in this one event, because when we get out a few more years, we expect that our subpolar North Atlantic prediction will still be pretty far off. So let's take a look at what happened at the beginning. So this is a gridded observational data set. Here's our forest ocean sea ice simulation. So this is where the DPLE's initial conditions are drawn from. And you can use this as a stand-in for truth because it's being driven very strongly by an atmosphere that looks like observations. And then this is our month 1 of what the predictions looked like. You can see that all of them have a cold blob in November 2014. We started from a cold state. And then the spread about the observations, which are indicated by the black line, and then this truth stand-in, the forest ocean sea ice simulation in red, are pretty tight, and they're all cold. We started out with a good initialization. But didn't last very long. So this is the ensemble mean and the Decadal Prediction Large Ensemble. Not only did we lose the cold blob, but it warmed up. And if we look at all 40 ensemble members in this histogram, not a single one was down near where the observations were, and only 3 ensemble members had negative sea surface temperatures. this was a pretty badly blown forecast for an initialization that looked okay. So what happened? Let's look at a time series for the subpolar North Atlantic sea surface temperature. The black line in solid is ERSST. The dashed line is the FOSI simulation, so the ocean-only strongly forced one. And then this gray spread is the DPLE, our prediction. You can see almost from the get-go that DPLE starts trending upwards, where the observations stay at half a degree C anomaly, and then decrease even further into the summer. So the real problem, it seems, is this upward trend. Why does, even when we've taken out all of the anomalies, why is the DPLE insisting on going upward? The cold blob was also not just at the surface, it extends down to about 1,000 meters. So here's one representation of the ocean heat content down to 300 meters. And so what you can see is that the EN4 ocean heat content, an observation-based product, shows that our initialization probably wasn't cold enough. The FOSI probably wasn't quite cold enough, but even it stays colder while the ensemble mean starts slowly warming back up. So something about the entire process that's going on are acting to warm up the subpolar North Atlantic. So we can use the processes in the forced ocean sea ice simulation, because it is driven by atmospheric reanalysis, to try to understand mechanistically what's happened. So here I've done an ocean heat budget analysis. Black line is the total heat tendency, and then we divided it up into 3 processes that all add back up to the total. Well, we have a negative. That should be something that's leading to an ocean cooling. That's what we're looking for. Positive indicates something that's warming the ocean up. So this orange line is the surface heat fluxes, and the blue line is resolved advection. And what you can see is that you both have strong negative anomalies of these two during January and March of 2015, and that those 2 months in particular are leading to a lot of the cooling. If we look at the DPLE, so those are the solid lines, and compare it towards the FOSI, our stand-in for truth, what we can see is that for both the surface heat fluxes on top and the advection below, the FOSI falls outside the spread of the DPLE in both January and March. So you're not getting ocean cooling due to both surface heat fluxes and due to ocean advection in those time periods. Because these are both monthly spikes, this points towards something in the atmosphere. Surface heat fluxes certainly sound like something in the atmosphere, and the ocean advection in this case is probably some sort of Ekman-related process, a wind-driven heat tendency. So let's take a look at the atmosphere. So what we've got here is November 2014 through May 2015. In shading, we have surface heat fluxes. Blue indicates cooling. That's what we're looking for. When was there cooling? And then the lines indicate sea level pressure. And those can be used like streamlines. They'll indicate what the atmosphere's wind is doing. So what you can see is you have really strong winds from west to east in January, December, and March. And those winds are associated with really strong upward surface heat fluxes. So you're cooling the ocean in December, January, and March due to the turbulent heat fluxes, or at least that's kind of what this look at the observations suggests. So let's now think about, what does the atmospheric circulation in the DPLE look like? Do we have an atmospheric circulation with strong winds across the subpolar North Atlantic in any of the ensemble members? So this is, I'm using a metric, the North Atlantic Oscillation, which is the first leading mode of climate variability in the atmosphere. So this is what the pattern looks like. So you can see it has a nice strong sea level pressure pattern, so strong winds across the subpolar North Atlantic. Gray and purple are the NAO in the DPLE, each of the ensemble members. And the black line is the observed NAO index. So you can see in January and March, you do indeed have a strong jet in the atmosphere at those times. But none of the ensemble members, if you average over 3 months, none of them have a consistent and very positive NAO as was observed. So this black line falls outside the spread So something that was very special about 2015 was just how positive the North Atlantic Oscillation was, and not a single of the ensemble members captured that. So this brings us to some of the meat of this study, which was trying to figure out, why did the DPLE not explain this? We've got a couple of hypotheses. One is that maybe the community Earth system model just doesn't do very well with these kind of events. Maybe there's some sort of model bias. It can't produce cold blobs. It can't produce very positive NAOs. The other possibility is that this was a very rare event. So the subpolar cold blob was near record. And the wintertime NAO, as you'll see in the next slide, this was the most positive wintertime NAO in the historic record that we have. Those are both incredibly rare events to have occurred. And then the third possibility is that there's something deficient in the initial conditions for the model. So let's address the first hypothesis first, that CESM cannot explain or cannot produce subpolar North Atlantic cold blobs or positive NAO conditions. So what we have here on the left is two histograms that are overlying each other. The orange histogram is the observed sea surface temperature in the subpolar North Atlantic and the frequency of occurrence in each of these bins. This black line here, gray, shows you where the observed 2015 cold blob fell. The purple histogram is the CESM Large Ensembles ensemble mean. And then the black bars indicate the spread of possible histograms you could get from all 40 ensemble members. So the bottom of the bar is the minimum frequency that you could have gotten in that bin from any one of those 40 ensemble members. And then the maximum is the maximum possible that you could have gotten. If the orange histogram, the observed, falls within those bars, then all we can say is that, to the best of our ability, the observations and the model are consistent. We cannot tell anything from this one view that they are different. If the orange falls outside our range of natural availability, then there's two possibilities. One is that what occurred in observations was quite rare, more rare than you could have modeled in 40 ensemble members, or that the model has a bias, that something is deficient in either structure of the model or something like that. For our 2015, so we care about the cold extremes, we can see that the observations fall within the spread of the natural variability that the model can produce. So all we can say is that they're likely consistent with each other. We don't have any immediate evidence to say that the model is doing something wrong. And then if we do the same exercise for the NAO, so here, this orange line up here, this is the observed NAO from 2015 in the winter. You can see that it's a very, very rare event, but that when we can use this huge set, the CESM Large Ensemble, we're using 40 ensemble members times 98 years. So we have quite a good sample, and we can see that the observed event in orange falls within our natural variability spread again. To the best of our ability, we, at least this cursory glance, it looks like the CESM is doing okay with producing both subpolar cold events and strong positive NAOs. Both are rare, but CESM can produce these kind of events. So we're going to get rid of that hypothesis that CESM just can't make a cold blob. Second possibility is that this was a very rare event. So from that histogram on the previous slide, if you did the math out, you would see that there's 1 out of every 50 winters in the CESM Large Ensemble has a cold event as cold as 2015. So maybe we just need to add another 10 ensemble members, number 20 ensemble members, and we'll get something cold. The NAO was very rare in the CESM Large Ensemble. 1 out of every 440 winters had an event as positive as that in 2015. So we aren't going to be adding that many more ensemble members to see if by chance we get a positive NAO. But that assumes, of course, that the NAO has no initial value predictability. And there's evidence out there that says that you can predict the NAO potentially out to about a year or beyond. So let's add some more ensemble members and see if we can get a cold blob. The red are a 20-member addition to this ensemble in this one initialization from 2014. You can see that we've added a couple of negative ensemble members, but none were as negative as the observations. And then the purple lines here are the additional 20 ensemble members. You have no additional ensemble members that get you an atmospheric state any more positive than what already occurred. And the fact that for sea surface temperature, the fact that the ensemble mean is positive, even though we're starting from a cold state, really suggests that something about the initial conditions is at fault. We can't, even if we add more ensemble members, it's going to be very difficult to increase the spread on the negative side down towards where the observations were. So it's a possible explanation that this was a very rare event, so it was going to be difficult to explain. But it's also more likely that there's something about the initial conditions that could have been better, that could have caused this prediction to go awry. And so I identified 3 initial condition related deficiencies in this one hindcast. First is that this hindcast in the first month has way too much Barents-Kara sea ice. And there's been a whole host of literature over the past 5 to 10 years showing how sea ice may or may not affect atmospheric circulation on these one-ish year timescales. The second issue is that the initial conditions for the upper ocean were both too warm and too fresh. And the third issue is that the atmospheric initial conditions, as I'll explain in a bit, aren't actually based on observations. And so while you expect the atmospheric initial conditions should only give you a couple of weeks of predictability, maybe that's not the case. So in the interest of time, I'm just going to tell you that the sea ice, we ran a sensitivity experiment where we changed up how the sea ice evolves in that first month to improve it, and it did not improve the prediction. So it's not related to Barents-Kara sea ice. The second piece is subpolar North Atlantic, the initial conditions. So here on top, we've got the upper ocean heat content in temperature, and then we've got salinity from EN4. You can see the real cold blob had anomalies going down to 500 meters and below. And not only did you have a cold blob at depth, it was also a fresh blob. So the CESM FOSI, which is what we draw our initial conditions from, was not cold enough. It was weakly cold, and it had a salty anomaly. Either of these issues could be part of it. Particularly maybe you had too salty of an anomaly, you affected the stratification and you messed up all of the coupled feedbacks for that reason. So what we're going to do, and by the way, this is what the actual DPLE looks like. It followed along much of what its initial conditions started with. So here you can see that it also has the salty anomaly, and that at the initial conditions in November, you also didn't have a cold anomaly at depth. So this is probably a big chunk of the problem. It just wasn't cold enough in the initial conditions. So what we're doing now is we're going to do an anomaly initialized simulation. We're going to take the anomalies from EN4 and use them in an experiment where we replace the initial conditions with the model's climatology plus temperature and salinity from observations. And we do this approach because if we put in raw temperature and salinity, its climatology, its attractor, is far from what the models might be. And that could cause a shock that would ruin the forecast. But by doing this anomaly initialized approach where we use the anomalies of temperature and salinity, we're hoping that you won't have as much of a shock. You can see that so we're starting from this cold anomaly. You can see there's a minor improvement. This simulation shows slightly colder anomalies, but they wear off. At least you've gotten rid of the warmth in the ensemble mean at the surface, but it still isn't as cold of an event as what occurred in observations. So this is a minor improvement, but it didn't do as much as we had hoped for improving this prediction. It did improve the freshness. But so it goes. So this issue with initial conditions, the upper ocean is still too warm and is still an issue. We don't know why the model can't sustain a cold condition. That's still up for future research. The second issue that we think might be a possibility is that the atmospheric initial conditions are drawn from CESM Large Ensemble. The reasons for that was because you have these restart files available that have all of the full fields that you need, whereas you don't have those fields available from an atmospheric reanalysis. And we also don't think that in most cases, atmospheric evolution driven by initial values really lasts more than a few weeks. So for 10-year timescales or 1-year timescales, we really don't think that should be a huge thing. But what we've done now is we've gone back and replaced the initial conditions with true observed initial conditions, or at least as observed as you can get from a reanalysis. And the startling thing here was that we had a way worse prediction when we only changed the atmospheric initial conditions to be what should have been closer to what was observed. So this orange line here is our new sensitivity experiment. The black line is the original prediction, the DPLE. Blue is the observations. You can see, even though the only thing we've changed is the atmospheric initial conditions, the sea surface temperature anomaly, the ocean, suddenly warmed back up within the first month from what occurred in the DPLE, which is pretty puzzling. So what happened was, in the DPLE, there are atmospheric initial conditions that drove in the first 2 weeks a really sharp cooling. And these came from the CESM Large Ensemble purely by chance. Just happened to be the type of initial conditions. And so this is an example of the right answer for the wrong reason. We started out in the right cold condition, but it happened to be from observational initial conditions that, well, they weren't observational. They were just what the CESM Large Ensemble had, and it just by chance cooled things off. And so this is a really important case of showing just the atmospheric initial conditions do matter on year-long timescales, especially if they affect the ocean's evolution, and that it is important to use initial conditions that are matched in the atmosphere, but that it's not going to be an easy solution to improve the prediction of this one case. So to summarize, systems like the CESM-Decadal Prediction Large Ensemble are actually showing pretty good skill out 10 years. But as I've shown in this one case study for the subpolar cold blob, there's still work to be done. These are experimental. We're not ready yet to, or at least that's my opinion, I don't think we're ready yet to be giving these to stakeholders and say, yeah, we trust what this is going to do. In this cold blob study, if you would give them the 2014 prediction, in the case of the subpolar North Atlantic, it would have been wrong. So this was a near record event. It impacted European climates. And there's been a whole host of studies on this one event. It's quite an interesting one. It was poorly predicted. So this case study was to try and figure out what went wrong. And we've identified that the NAO was not predicted. So these two things are linked. So we tried to look at a bunch of different possible pieces of the climate that could fit the NAO. So that included ocean heat content and sea ice, as well as the initial atmospheric initial conditions. And we still haven't been able to figure out exactly how we can make this event predicted. But this has been very helpful for us to test out different possibilities for the next set of decadal predictions that NCAR will produce. And so this has been a very useful case study. There's others at NCAR who are continuing on this work with different initialization methods. For example, my friend Dan Amrine, I think he's going to use this as a case study for using data assimilation to produce a better initial state. So the name of the talk was, can you predict this event? So we've looked in one model and seen, well, maybe not in this model. Something's really not working. I've been also working on a multi-model decadal prediction case study of this event using 5 different systems from our Blue Action European partners. And 2 of these 5 prediction systems that I've examined so far do have a weak cold blob that they were able to predict during summer 2015. Neither is as cold as observed, but it does look like in other systems you can predict this event. And so the work that needs to be done now something I was working on this morning, is trying to figure out, is there anything in common between the 2 models that were able to predict this event and the 3 remaining that were unable. And so I'm looking forward to working on that over the next couple of months, and maybe I'll post on Twitter at some time with what happens. So again, thank you so much for your time and for listening, and I look forward to hearing any feedback or questions you may have.
That was great, Elizabeth. I learned a lot. We now do questions and answers. And what I like to do is ask for questions from students first. So if there are any students out there who have questions for Elizabeth, please raise your hand. Any students? Okay, Luis.
Oh, hello. First of all, I think your research is pretty amazing, I have to say. Can you talk a little bit about the components of your system of prediction? So you mentioned like it's like a comprehensive ocean atmosphere, but if you can like talk a little bit more about that.
Sure. So this version of CESM1, it's specifically, I think, version 1.2.2. The atmosphere is the community atmosphere model version 5, CAM. It has, I think, it's pretty similar to CAM 4, but I think it has a more updated version of the aerosol physics than CAM 4 had. The ocean is the Portable Ocean Model 2, POP2. POP2 is, I'm trying to remember exactly the dynamics in there. I think between POP2 and the most recent version of CESM, the big addition has been an estuary box model that's not included. But that's the ocean model. I think it uses SICE for the sea ice, and then it uses not LM2, that's the GFDL model that I used to work with. The community land model, which has a bunch of different vegetation classes. And so those are all the components that are then coupled together by, they had a fun name for the coupler in this version that I'm totally blanking on right now. But the resolution, the atmosphere in the ocean is roughly about 1 degree. So fairly coarse. These are standard resolutions for climate models, such as used for CMIP or the IPCC's versions. Something fun is that sometime in the next couple of years, I think one of the next decadal prediction sets from NCAR will be probably using their 0.25 or 0.1 degree ocean. So you'll really start resolving and permitting eddies, which could make a huge difference in some of these predictions. So they won't be the first to make a prediction set at that level. The British I think the Met Office beat them to it. They have a high resolution ocean set. Does that kind of answer your question? Are there any specific of the components you had more questions on?
No, actually, just like was curious. Like I said, that was like pretty good for me for what I was asking for. I have another quick question, if like you don't mind. Like so far, like what do you think is the more like problematic issue with like climate modeling?
Oh, there's a question. That's a whole field. Problematic issues with climate modeling. Well, the fact that coarse ocean models don't resolve eddies, that's a big one. So they have parameterizations, so Jen McWilliams ready parameterization to try to get at that, but those are imperfect. And so I'm really excited to see some of the new high resolution coupled ocean atmosphere studies that are coming out, particularly the ones from NCAR, since those are the ones I'm most familiar with. So that's definitely an area that excites me. The other issue is, which I bet you're referring to, is the idea of tuning. When you put together these models and you couple them all together, you're starting out from like 4 or 5 teams. You have a team on the atmosphere, you have a team on the ocean, a team on the land and ice, and they work independently and they say, okay, we've got a good atmosphere, we've got a good ocean, let's throw them all together. And when they do that, your first run through, you have a really terrible climate. It doesn't look at all like the observed Earth. And what happened while I was at NCAR, so I was there while they were preparing the CMIP 6 version. And it took them a year or two to figure out why they kept getting a freeze over of the Labrador Sea. So no matter what they did with changing the tuning in each of these models, the Labrador Sea kept freezing over. And that's bad because once the Labrador Sea in that model freezes over, the entire globe will go towards snowball Earth within a couple of decades. And very clearly, we don't live in a snowball Earth world. So there was something about the model that just, you know, didn't like it. And it actually wasn't even every time. It was 3 out of 4 runs would go that direction. And so this brings up the idea of tuning. How do you figure out how to tune all of these models individually and then put them all together and then retune them such that you are using parameters that we think are like the observed world's parameters? So by parameters, I think mean like albedo of clouds, albedo of ocean. For the ocean, like the parameterization of how you think the eddies work. So the diffusivity constants, things like that. How do you tune those appropriately in a physical way? And it's really hard. And you need people like the scientists at NCAR and at GFDL who really know how the models work almost at an intuitive level and know how to turn the knobs. But then you invite the criticism of, well, you're just turning the knobs to match the observed climate, and they're not physically, that's not physically a good way to do things. So there's a whole field of study of people who try to figure this out, especially at the modeling centers, and it's problematic, but it's part of how climate modeling has to work. So maybe that was a long answer for your question, but those are 2 things I think about a lot.
Thanks a lot. That was perfect. I was talking about the tuning. I know it can be like a huge issue.
Oh yeah, being at NCAR, it was like watching how the sausage was made when I was there. It was just the right time. It was fascinating. I learned a ton.
Again, thanks a lot. Your talk was awesome.
Okay, do we have any other student questions before we open it up? Okay, let's open it up to everybody. If anyone has a question, please raise your hand. Okay, Boris.
All right. It was interesting presentation, and I also learned a lot from it. But I have a question. First of all, I noticed that you showed us maps of salinity and temperature, but you didn't talk about the dynamics, what velocities are doing, what eddy kinetic energy is doing, are they in good agreement or not? You cannot talk about dynamics without looking into velocities. So this is a real big missing puzzle in this. Another thing, the velocity is responsible for mixing. So it's not only diffusivity coefficient, it's also viscosity coefficient. And what I see in your inability to predict this blob is you just have too much diffusivity or too much viscosity, and you need a better parameterization for it. It's true that eddies have a big effect on it, and resolution of 1 degree, it's very difficult to do it. And I suspect that all these models you use, they use constant viscosity and constant diffusivity, and this is not a good model for mixing processes. So, you know, as long as you do mixing with constant coefficients, you will never be able to improve that much. You can do it some better job with data assimilation and better initial conditions, but the dynamics will catch up with you after some time.
So that's true. Yes, there are a lot of deficiencies in an ocean model of this resolution, but that doesn't mean that you can't use it to predict something from the full climate system. So 63 out of the 64 initializations we had, it was a successful prediction. So there is something that you can say, even with all the deficiencies in a climate model of this resolution. And I'm looking forward to seeing, as the parameterizations get more advanced in this class of models, how that improves things. But the computational expense for just this one system was something like millions of core hours. increasing the resolution, improving the parameterizations such for an increased resolution model is just not quite within our grasp yet. With your first part of the question, I haven't looked as much at the direct U and V. I did look a little bit at the mixing. There's a lot of really fun mixing diagnostics that are available, and I quickly it went in circles between what part of the mixing and what part of the diffusion processes were causing the warming or the cooling, and there was nothing I could tell very clearly about it. The clearest signal we were able to find was that you weren't getting enough heating because the atmosphere above was just way too weak. You just weren't driving enough.
And you may have the same problem of mixing in the atmospheric model as well.
Oh yeah, very possibly. Boundary layer processes need more work.
Yes, I agree. All right, thank you.
Brad, I see your hand up. Boris, you can put your hand down.
Never.
I'm sure Boris has many more questions, right? Thank you for the talk, Elizabeth. I wanted to ask about at one point you stated that this model is getting pretty good at looking forward at about decadal scale. And I wanted to ask sort of a two-part question based on as you go along every year and get more data to run the hindcast with, will that improve that range of time that you can look forward to? Sort of question number one. And then question number two, I think it might be a slightly different answer, but as you average more hindcast data, does it actually impede your ability to look at these regional extreme events because you kind of average them out in the hindcast data?
So the way that the initialization occurs in this model is, so you're describing like a data assimilation approach where you see what's going on back a year and then 9 months and 6 months and sort of grabbing it all together. And this isn't, the initialization for this wasn't even that sophisticated. It was literally, we have the forced ocean simulation. You create a restart file of all of the ocean and the oceanic field and grab those on day one. And so this is some of the things that they're trying out is they're going to try an ensemble Kalman filter approach to see if that improves things or not. There's a lot of different ways you can initialize these systems with like anomaly approaches and then incorporating data assimilation or using the full field, kind of like this approach uses. The full field is nice because we're using something that we think is closer to the full coupled systems attractor. But, you know, the ocean only model is not the same thing as the fully coupled model. Mm-hmm. But yeah, there's a lot of work to be done. They're still doing that over at NCAR, and I'm still trying to sort of tag along as best I can from 1,000 miles away.
Right. Thank you.
Excellent. I see Alex Illich, you have your hand up. Another student, yay.
Hi, great talk. So I'm not super familiar with all this stuff, but I was just wondering to some extent, like, how much is this the nature of predictive modeling? Like you showed kind of the expected mean trend with some uncertainty around it, and then that Atlantic cold blob is well outside. But, you know, with statistical models, if you have like your uncertainty as a 95% confidence interval, you'd expect every once in a while, about 5%, it's going to fall outside of that range. So is it just kind of the nature of predictive modeling that when you have those extreme events, you know, every so often you're going to end outside of the confidence intervals just by sheer probability?
Yes, that is one possibility. That just, it was a very rare event and you just couldn't predict it. It's unpredictable, and that is a perfectly acceptable answer potentially. But that it ignores if there's any initial value predictability that's possible. And in this event, we, at least in the subpolar North Atlantic, we started out with the initial values, at least at the surface, in the right place. And the fact that we lost all of that initial value predictability that quickly really suggests that there was something wrong about the initial conditions as well. We should have had at least one ensemble member that was that cold, but most of them were too warm. But yeah, you're absolutely right. Some of these events are unpredictable, and that might be an acceptable answer.
Okay, thank you.
Oh, Sorry. Brad, is your hand still up or did you just forget? Does anyone else have any questions?
I just forgot, sorry.
No worries. Anybody else? We're about 5 minutes over. But if anyone has any questions, we can continue on. And if not, we can all open up our mics and thank Elizabeth, which I think we should probably do. And
thanks.
That was really great. I learned a ton about climate models, and I hope that all of our guests did too. And yeah, it was really great, especially after I spent all day writing a perspective for science on how the North Atlantic may not be the be-all and the end-all of climate forcing. So wait for that.
Thanks again for the invitation. I really wish that I could be there in person with you all, maybe someday in a few years.
Yeah, I really appreciate it. It was great hearing this. We don't get a lot of seminars like this, and we should really get more, and I learned a ton. So thank you. And stay safe in Wisconsin.
Thanks, you too.
Bye-bye.